Welcome to today's session. In this video, we'll explore a fascinating problem from LeetCode, problem number 980, titled Unique Paths 3. This problem challenges us to find all unique paths from a start point to an end point while visiting every square on a grid exactly once. Get ready to dive into the world of algorithmic problem solving as we analyze the steps and approaches to tackle this problem. In this problem, we are tasked with navigating a grid to find all unique paths that meet certain criteria. The grid is represented as a 2D array, where each cell has a specific meaning. A cell with the value 1 is the starting square, and there is exactly one such square in the grid. Similarly, a cell with the value 2 is the ending square, and there is exactly one of these as well. Cells with the value 0 are empty squares, and these are squares we can walk over. Finally, cells with the value -1 are obstacles, which we cannot traverse. The goal is to determine the number of valid paths from the starting square to the ending square, under the condition that every non-obstacle square is visited exactly once. Additionally, movement is restricted to 4 directions: up, down, left, and right. To better understand the problem, let's look at an example. Consider this grid. We start at the top left corner, represented by the value 1, and aim to reach the bottom right corner, represented by the value 2. Along the way, we must visit every empty square, marked as 0, exactly once, while avoiding the obstacle, which is represented by -1. For this specific input, there are 2 valid paths that meet the criteria. The first path involves moving right across the top row, down to the bottom row, and then navigating through all remaining empty squares to reach the ending square. The second path starts by moving downward first, then traversing across the grid while still visiting each empty square exactly once. Both paths end at the same destination, and therefore, the output for this example is 2. Now, let's examine another example. In this case, the grid does not contain any obstacles. Starting at the top left corner, there are 4 possible unique paths that visit all empty squares exactly once and end at the bottom right corner. This is because the absence of obstacles allows for more flexibility in how we navigate through the grid. However, every valid path still adheres to the rule of visiting each empty square only once before reaching the endpoint. On the other hand, if we consider a smaller grid, such as a 2x2 grid where the start and end squares are diagonally opposite, it's possible for no valid paths to exist. For instance, if there's no route that allows us to visit all empty squares exactly once, the output would simply be 0. It's also important to evaluate the problem under specific constraints and edge cases. The grid dimensions, represented by m and n, must satisfy the condition that both are between 1 and 20 inclusive, with the total number of cells not exceeding 20. The values within the grid are restricted to -1, 0, 1, or 2, and there must be exactly one starting square and one ending square. For edge cases, consider a grid filled entirely with obstacles except for the start and end squares. In such a scenario, there's no valid path, and the output would be 0. Similarly, if the start and end squares are not connected or there are unreachable empty squares, the result is also 0. Finally, a grid with no obstacles and only empty squares would yield the maximum number of valid paths, limited by the grid size. These constraints and examples help clarify the problem's requirements and guide us in designing an efficient solution. To solve this problem, we need to find all unique paths from the start square to the end square, ensuring every empty square is visited exactly once. A straightforward way to approach this is through a brute force method, which involves exhaustive search. The idea here is to generate all possible paths starting from the given start square. We can use backtracking to explore each path, maintaining a set of visited squares to ensure no square is visited more than once. If a path satisfies the conditions ending at the target square and visiting all empty squares, it's counted as valid. However, this approach has significant drawbacks. The search space grows exponentially with the number of empty squares, leading to a time complexity of 4 to the power of k, where k is the number of empty squares. Additionally, this method is inefficient for larger grids because it repeatedly explores invalid or redundant paths, making it impractical in many cases. To overcome the inefficiencies of brute force, we can use an optimized backtracking approach with pruning. Instead of blindly exploring all paths, we strategically eliminate paths that cannot possibly lead to valid solutions. This is achieved by leveraging problem constraints, such as the fixed total number of steps required to visit each square exactly once. By pruning paths that revisit squares or exceed the required step count, we significantly reduce redundant computations. Here's how we implement this approach. First, we count the total number of empty squares, including the starting square. Then, we perform a depth-first search from the start square. At each step, the current square is marked as visited, and we recursively explore its valid neighbors, those that are within bounds, not obstacles, and unvisited. After exploring all options for a square, it's unmarked to allow for backtracking. If the end square is reached and all empty squares have been visited, this path is counted as valid. This systematic process ensures we explore only potential solutions while avoiding wasted effort on invalid paths. The complexity of this optimized approach remains 4 to the power of k, in the worst case, where k is the number of empty squares, but pruning significantly reduces the number of paths explored compared to brute force. The space complexity is m*n, accounting for the recursion stack and the visited state of the grid. While the approach is still exponential, it is practical for small to medium grid sizes and avoids the inefficiencies of brute force. However, there are trade-offs. Careful implementation is needed to avoid revisiting nodes unnecessarily, which could negate the benefits of pruning. As for alternatives, dynamic programming is typically effective for simpler unique paths problems but isn't feasible here due to the constraint of visiting every square exactly once. Breadth-first search is another option, but it's less suitable because it requires higher memory usage and struggles to handle the strict path constraints efficiently. Given the problem's constraints, backtracking with pruning is the most appropriate strategy. It directly addresses the requirement to visit all empty squares exactly once while minimizing redundant computations. Compared to brute force, this method is far more efficient, and it avoids the high memory overhead associated with BFS. By balancing computational feasibility and correctness, this approach is both practical and effective for solving the problem. It ensures that we can handle small to medium grid sizes while adhering to all constraints, making it the optimal choice in this scenario. To solve the problem of finding all unique paths from the starting square to the ending square while visiting every empty square exactly once, we use a brute force approach based on backtracking. First, we need to parse the input grid and locate the starting square, ending square, and all empty squares. During this setup, we also count the total number of squares that need to be visited, including the starting square. Next, we define the 4 possible directions of movement up, down, left, and right using a list of tuples. This helps us systematically explore all neighboring squares during the algorithm. We then define a recursive backtracking function that explores all possible paths from the current square. This function takes the current position, x, y, and the count of visited squares as inputs. Base cases are crucial here. If the current position is out of bounds, an obstacle, or invalid in any way, the function terminates. When the ending square is reached, the algorithm checks if the number of visited squares matches the required total. If they match, we increment a global variable, path_count, which keeps track of valid paths. Otherwise, the function proceeds to recursively explore all possible directions by marking the current square as visited, moving to neighboring squares, and backtracking by resetting the square to its original state once all paths are explored. To initiate the process, the backtracking function is called from the starting square with the visited count set to 1. The algorithm then systematically explores all possible paths through recursive calls. Once all paths have been explored, the value of path_count is returned as the final result, representing the total number of unique valid paths. Backtracking serves as the core framework here, allowing us to make choices, explore possible paths, and undo those choices when necessary. This ensures that every possibility is considered while adhering to the constraints. The constraints themselves, such as avoiding obstacles and ensuring we visit every square, are handled naturally through the base cases and recursion. The algorithm validates paths only when the ending square is reached, ensuring that invalid paths are excluded. This guarantees that only those paths where all empty squares are visited contribute to the result. The main data structure used is the grid itself, which is modified in place to mark and unmark squares during the search. A global counter, path_count, helps in keeping track of the number of valid paths. Additionally, the predefined direction list streamlines the movement logic by providing a consistent way to explore neighboring squares. Several key operations are performed during the backtracking process. Marking a square as visited by temporarily setting its value to -1 ensures that cells are not revisited within a single path. After all possible paths from a square are explored, the square is unmarked to restore its original state, allowing it to be part of other paths. Recursive calls represent moving to the next step in a path, with the depth of recursion limited by the number of empty squares. Boundary and constraint checks, such as verifying whether a move is valid or whether a square is an obstacle, ensure that the algorithm avoids unnecessary computations and remains efficient. Finally, let's analyze the complexity of this algorithm. In the worst case, the algorithm explores all permutations of empty squares. If there are k empty squares, the time complexity is approximately 4 to the power of k, since there are 4 potential moves from each square. As for space complexity, the maximum depth of the recursion stack is equal to the number of empty squares, resulting in a space complexity of k. While this complexity might seem high, it is acceptable for small grid sizes, which is typical for this type of problem. Here, we start by defining the unique paths III function within the solution class. The first step is to determine the dimensions of the grid and initialize some variables. Rows and calls hold the number of rows and columns, respectively. We also initialize empty underscore squares to count the number of walkable squares, while start_x, start_y, end_x, and end_y will store the coordinates of the starting and ending points. Next, we iterate through the grid using nested loops. If we encounter a1, it marks the starting square, so we capture its coordinates. A2 indicates the ending square, and we store those coordinates as well. For 0, we increment the empty underscore squares counter since these are squares we need to traverse. After identifying the grid's key features, we define a helper function DFS for depth first search. This function will explore all possible paths recursively. The base case checks if we've reached the ending square. If the remaining squares to visit is exactly -1, it means we've covered all required squares, so we return 1 to count this as a valid path. Otherwise, we return 0. Before exploring further, we mark the current square as visited by setting its value to -1 to avoid revisiting it during the same search path. The exploration continues with a loop that checks all 4 possible directions: right, down, left, and up. For each direction, we calculate the new coordinates nx in New York. We then verify that these coordinates are within the grid boundaries and lead to either an unvisited square, 0, or the ending square, 2. If the conditions are met, we recursively call the DFS function, reducing the remaining count by 1 as we move to the next square. After exploring all possible paths from the current square, we backtrack by unmarking it, setting its value back to 0, to allow it to be used in other potential paths. Finally, the DFS function counts and returns the total number of valid paths found. To initiate the search, we call DFS starting from the coordinates of the starting square and pass empty underscore squares plus 1 as the number of remaining squares to traverse, which includes the start and end squares. This ensures that every unique path is counted while adhering to the problem's constraints. Here, we begin by defining the unique paths IIA method, which takes the grid as input. The first step is to initialize some variables, rows and calls to represent the dimensions of the grid, empty squares to count the number of cells we need to visit, and coordinates for the start and end points. Next, we loop through each cell in the grid to identify the starting square, the ending square, and count the empty squares. If a cell contains the value 1, it marks our starting point, so we store its coordinates in start_x and start_y. Similarly, if the cell value is 2, it represents the endpoint, and we store those coordinates in end_x and end_y. For any cell with a 0, we increment the empty squares count since these are the traversable cells. After gathering this information, we call the depth first search, or DFS, method starting from the start_x and start_y, passing along the total number of empty squares plus 1 to account for the endpoint, as well as the endpoint coordinates. The DFS method is where we perform the recursive exploration of all possible paths. First, we handle the base case. If the current square matches the endpoint coordinates, we check if all required squares have been visited. If remaining equals -1, it means we've visited every square exactly once, and we return 1 to count this as a valid path. Otherwise, we return 0. Next, we mark the current square as visited by setting its value to -1, preventing revisits during this recursive call. We then define the 4 possible movement directions: right, down, left, and up. Using a loop, we explore each direction and calculate the new coordinates. For each new position, we check if it's within the grid boundaries and is either an empty square or the endpoint. If valid, we recursively call DFS, decrementing the remaining count. After exploring all directions, we backtrack by resetting the square to 0, allowing it to be revisited in other paths. Finally, we return the total paths found from this square. In this example, we start with a simple grid where the path has no obstacles. The grid has 1 row and 4 columns. Our starting point is located at the top left corner, 0, 0, and the end point is at 0, 3. There are 2 empty squares between the start and end. First, we initialize key variables: the grid dimensions, the number of empty squares, and the coordinates of the start and end points. Then, we begin our depth-first search, or DFS, from the start position, 0, 0. Here, we have 3 squares to visit, including the starting point. We mark the start as visited by modifying the grid value to -1 and proceed to explore adjacent cells. Moving right to 0, 1, we decrement the remaining count to 2, mark the square as visited, and continue moving right to 0, 2. From here, we move to 0, 3, the endpoint, with no remaining squares left to visit, making this a valid path. Upon reaching the endpoint, we confirm that all squares have been visited exactly once. This means we have found one unique path. After recording this path, we backtrack by unmarking the squares 0, 2, and 0, 1 to return the grid to its original state. Backtracking ensures that we can explore other potential paths, though in this case, no additional moves are possible from the starting point. Finally, we calculate the total number of unique paths, which is 1 for this example. The output for this input grid is therefore 1. Now, let's look at a slightly more complex grid that includes an obstacle. In this second example, the grid has 2 rows and 3 columns, with an obstacle denoted by -1. The starting position is again the top left corner, 0, 0, and the endpoint is at the bottom right corner, 1, 2. There are 3 empty squares to visit. We initialize the variables, then start the DFS at 0, 0, with 4 squares remaining, including the starting point. The start is marked as visited, and we explore its neighbors. Moving down to 1, 0, we decrement the remaining count to 3, mark this square as visited, and then move right to 1, 1. Here, we again decrement the count, mark 1, 1 as visited, and proceed to 1, 2. At this point, we reach the endpoint with exactly 0 remaining squares, making this a valid path. Once we find the valid path, we backtrack to explore other possibilities. We unmark 1, 1, and 1, 0 as visited, returning to the original grid state. However, there are no other valid moves from the starting point, 0, 0, due to the obstacle blocking access to the top right corner. Thus, the total number of unique paths for this grid is also 1. The output for this input is 1. Now, let's consider a scenario where no valid path exists due to obstacles completely blocking the way. In the third example, the grid consists of 2 rows and 2 columns, but the presence of obstacles prevents any valid path. The start is at 0, 0, and the endpoint is at 1, 1, with no empty squares to visit. After initializing the variables, we start the DFS from 0, 0, with only 1 square to visit, including the start. We mark 0, 0 as visited, but all adjacent squares are either obstacles or out of bounds. This means there are no valid moves, and the DFS terminates immediately. As a result, the total number of unique paths is 0, and the output for this input grid is 0. To analyze the time complexity of this solution, let's start by examining the depth-first search, or DFS, process. The DFS function explores all possible paths starting from the initial square and attempts to visit every empty square exactly once. At each recursive call, the algorithm checks up to 4 neighboring cells, provided they are valid moves. The recursion depth is determined by the total number of traversable squares in the grid, which includes the starting square, the ending square, and all empty squares. If we denote the total number of traversable squares as t, then the number of recursive calls grows exponentially with t. This results in a worst-case time complexity of O(4 to the power of t). Additionally, while the total grid size is defined by the number of rows and columns, n equals rows * calls, the key factor driving the exponential growth in recursive calls is the number of traversable squares, rather than the entire grid size. In the worst-case scenario, where every cell in the grid is traversable, t equals the total number of cells, n. This means the time complexity reaches its upper bound of O, 4 to the power of t, or O, 4 to the power of n. However, the presence of obstacles in the grid reduces the number of valid paths, effectively lowering t and mitigating the exponential growth. On the other hand, in the best-case scenario, where there are very few traversable squares, such as when most of the grid is occupied by obstacles, the time complexity becomes much smaller. For small grids with minimal traversable cells, the time complexity can even approach 1. Now, for space complexity, the main factor is the recursive call stack. The maximum recursion depth corresponds to the number of traversable squares, so the space used by the call stack is O, t, or equivalently, O, empty_squares plus 2. The grid itself is modified in place during the DFS process to mark cells as visited, which means no additional space is allocated for the grid, making the solution space efficient. In terms of auxiliary space, only a constant amount of memory is needed for variables such as rows, calls, and empty_squares. This means the overall space complexity remains dominated by the recursive call stack, keeping it at O, t, or O, empty_squares plus 2. Comparing this backtracking approach to a brute force solution highlights its efficiency. A brute force method would enumerate all possible paths in the grid without eliminating invalid ones early, leading to redundant computations and exponential growth. Backtracking, on the other hand, optimizes the search by marking cells as visited and unvisited in place, ensuring that only valid paths are explored. This significantly reduces redundant computations, making the current implementation much more time and space efficient. When analyzing the best and worst cases, the distinction becomes clear. In the best case, where there are many obstacles and only a few traversable squares, the recursion depth remains small, and the time complexity approaches 1 for small grids. On the flip side, in the worst-case scenario where all cells are traversable, the recursion depth reaches its maximum, and the recursive calls grow exponentially. This results in the upper bound of 4 to the power of n, for time complexity. Mathematically, since each cell can potentially lead to up to 4 neighbors, the total number of recursive calls grows as 4t, where t is the number of traversable cells. Therefore, the time complexity is capped at 4 to the power of t, while the space complexity remains at t, due to the recursive stack depth. This balance between the worst and best cases highlights the efficiency of the backtracking approach in managing both time and space requirements. One of the most common mistakes in solving unique paths 3 is not accounting for all empty squares. Remember, the problem specifically requires visiting every empty square exactly once. Skipping or revisiting any square results in an invalid path, so it's essential to track your progress accurately. Another pitfall is ignoring edge cases. For example, small grids like 1 by 1, grids with no valid paths, or scenarios where the start or end square is blocked. If these cases aren't handled properly, your solution might crash or produce incorrect results. Additionally, in recursive solutions, a poorly defined base case can lead to infinite recursion. For instance, if you forget to terminate when reaching the end square under valid conditions, it could cause a stack overflow. Finally, inefficient backtracking implementation is another issue. Modifying the grid in place without restoring its state can corrupt the grid for subsequent recursive calls. Always ensure the grid is restored after exploring a path to maintain its integrity for other recursive branches. Misunderstanding the problem constraints can also lead to issues. For example, assuming all grids are solvable or overlooking the grid size limit, which can be as large as 20 by 20, might result in overly complex or incorrect solutions. On the bright side, this problem offers valuable insights for interviews. It's a great example of applying pattern recognition to identify when pathfinding and backtracking techniques, such as depth-first search, are appropriate. A well-designed recursive function is critical. Clearly define parameters like the current position and the count of visited squares, and ensure your base cases are well thought out. This not only makes your solution cleaner but also avoids unnecessary computations. Testing thoroughly is another key point. Interviewers often introduce edge cases, like grids with obstacles, grids with no valid paths, or grids with unusual dimensions. Preparing for these scenarios will set you up for success. Another important aspect to prepare for is analyzing the space and time complexity of your solution. Since backtracking has an exponential nature, the worst-case time complexity for a grid of size m by n can be O, for caret, m*n. This highlights the importance of optimizing your approach wherever possible. In terms of related problems, LeetCode 79, word search, is a good example of a similar backtracking problem that involves grid traversal. LeetCode 200, number of islands, focuses on exploring connected components in a grid, which is another common grid-based challenge. LeetCode 130, surrounded regions, involves grid traversal using DFS or BFS, and of course, LeetCode 980 itself is a direct reference point for understanding variations of unique paths 3. Studying these problems can help you build a strong foundation in solving similar challenges. There are also alternative approaches to solving this problem. The brute force method, or exhaustive search, involves exploring all possible paths from the start to the end. While this approach is simple to implement, it becomes highly inefficient as the grid size increases due to the exponential growth in paths. A more practical approach is optimized backtracking. By employing pruning techniques, you can eliminate paths early if it becomes clear they can't lead to a valid solution, for instance, if visiting all empty squares becomes impossible. While this requires careful implementation, it significantly reduces unnecessary computations. Lastly, dynamic programming, though less common for this exact problem, can be applied to simpler variations where constraints like visiting every square don't apply. However, enforcing the visit every square condition complicates pure DP solutions. Each of these approaches has trade-offs, so it's important to choose the one that best fits the problem's requirements. Great job following along. To wrap up, we summarized the key points of the problem, including the brute force approach and the insights we gained about grid traversal and recursion. Remember, practicing these types of problems is invaluable for improving your algorithmic thinking. Thank you for watching, and don't forget to like, share, and subscribe. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!